there, Chris Clements again with another podcast. This one is on periodicity. We're going to go over some guys who invented the periodic table, groups, which are columns on the periodic table, trends within groups, and periods going from left to right, and then we'll talk about how elements are created. So let's start with the guys. There are three folks who are recognized for setting up the periodic table that we know about by now. The guy that you've probably heard of is Dmitri Mendeleev. He was a very well-recognized gentleman who was Russian, and what he ended up doing was organizing the elements according to their atomic mass, meaning what we would probably consider as average atomic mass. So his periodic table appeared in 1869. It was published. He was kind of a bigwig who got everything arranged. He had some blank spots, of course, because a lot of elements were not discovered by then, so he would think about it and put EKA, which means similar, in front of a name of another existing element, as in eka-silicon. He had a blank space beneath silicon, and he called that element eka-silicon. And he predicted the melting point and the mass of that element, and it ended up being germanium, pretty darn close to predicting the mass and the melting point. So he did a pretty good job. And a gentleman you've probably not heard of, Lothar Meyer, is a German gentleman who arranged his periodic table according to atomic volume. Not dissimilar to Mendeleev's by any means. Where Mendeleev had mass, Meyer had volume. He just didn't quite get the jump on it like Mendeleev did, so he is rarely credited with coming up with a periodic table. And then there's a gentleman you've probably not heard of either named Henry Moseley, a British gentleman who was a student of Ernest Rutherford, the gentleman who did the gold foil experiment that actually accidentally disproved the plum pudding model. He used a technique known as X-ray diffraction to end up determining atomic number, meaning the number of protons that are present in an atom. And he suggested arranging the periodic table, or the elements, in order of increasing atomic number. You'll notice your periodic table is currently arranged in that manner, where atomic number starts at 1 for hydrogen and goes up sequentially by 1 through all of the elements that currently exist. He did this at a very young age and ended up passing away at a very young age, as he died in 1915 at 27 years of age when he was fighting in the Battle of Gallipoli. A little tidbit there is that Great Britain then decided that no scientist would be called into battle ever again, and to my knowledge, no one ever has. Alrighty, let's move on to the groups of elements. We're going to start with hydrogen. Hydrogen, granted, is in group 1, the leftmost group, but it's kind of in a group of its own. It's not really like anyone else in group 1 because it's not a metal. It is like them in that it has one valence electron, though, so that's really why it's placed there. Hydrogen is a nonmetal. It's highly reactive because it has that one valence electron. It wants to get one more to look like helium or lose that one valence electron so that it's just a proton. It's the most abundant element in the universe. We move on to the rest of the elements in group 1, which are classified as the alkali metals. Those alkali metals are soft enough to be cut with a dull knife. They're about the consistency of cold butter. They are highly reactive, just like hydrogen is, again, because they are just one little electron away from being a noble gas. If they can all lithium, sodium, potassium, etc., if they can all just lose one electron, they'll look like the noble gas that precedes them. So that's what they end up doing. They really like to react with water, and if you think of water as not being H2O, but as being HOH, what these alkali metals will do is end up replacing the first H in HOH, kicking that H out. H doesn't like to live by itself, so it lives as H2, and that ends up producing a metal hydroxide. So, for example, if I stick potassium into water, I get KOH, and H2 gas. There's also a lot of heat generated in that reaction, so it's called an exothermic reaction for that reason. And heat and hydrogen gas get along very well. In fact, they really like to react and create a little boom, or a big boom, as it were. They're called alkali metals because they do make basic solutions when they're put in water in the form. The example I just gave you was KOH. They tend to be very good conductors of electricity. An example that you can see on street lamps is, if you see the orangish, yellowish glow of some street lamps, that's showing you that it contains sodium. ions in it, and those sodium ions, when they get excited and then fall back down to their ground state, they end up giving off yellowish orangish light, as those of you who've done flame tests have seen before. And as I stated before, they all have one valence electron. Group 2 elements are known as the alkaline earth metals. They tend to be harder than the alkali metals. They are reactive as well, but not as reactive as the alkali metals because of their number of valence electrons. They also can make basic solutions in water, hence their name alkaline earth metals. They tend to be found in the earth, as their name indicates as well. They are generally found in compounds that have structural integrity or a lot of oomph to them, things like emeralds, which are obviously pretty hard stones, gemstones, have beryllium in them. A lot of aircraft skins are made with magnesium. Marble has calcium in it. Bones have calcium. They do have 2 valence electrons, and that means they would tend to like to get rid of 2 valence electrons to end up being like the noble gas that precedes them. The next group is really a collection of groups. It's groups 3 through 12, which are known in an older style of nomenclature as the B elements. These are the transition metals. They are harder than groups 1 and 2 metals. They don't tend to be as reactive as groups 1 and 2 metals. Some obviously can react, but they are not classified as being highly reactive by any means. They are called transition metals because they kind of are transitive. They move all over the place. That means they have varying properties. They are very good conductors of heat and electricity. Hence, something like copper is used in wires for electrical components. And they are all solid at room temperature except, oh yeah, you guessed it, mercury. All of them are naturally occurring, we're going to say at this point, except technetium. That brings us to the next goofy group of elements, the lanthanide actinide series, which are known as the inner transition metals. They are actually 2 periods that live beneath the 7th period that are brought out so that the periodic table is not as wide as it would otherwise be. I'm just going to talk about the lanthanides as a group, even though it is a period, and the actinides as a group. The lanthanides are shiny and reactive. Some of them prove to have great uses. For example, neodymium is used in magnets. It is a very powerful magnet, much more so than a ferro or iron magnet is. You can use a smaller neodymium magnet in place of a ferromagnet and even get more magnetism yielded. Little tidbit on neodymium is that praseodymium and neodymium were once thought to be the same element. And someone, I don't remember who, obviously, discovered that they were actually 2 elements making up this thought to be one element. And they therefore named it neodymium, neo meaning new. Praseodymium means green twig, neodymium means new twig. Woohoo, cocktail information. Alrighty. The next group of elements we're going to talk about is not truly a group either. It's the metalloids. Those metalloids are the elements that are wishy-washy, have some metallic properties, some non-metallic properties. Some of them are considered to be more metal than others. I'm going to give you the ones that are truly considered to be metalloids. Those are boron, silicon, germanium, arsenic, antimony, and tellurium. They tend to be classified as semiconductors. That means that they'll conduct electricity at some times, typically under certain temperature conditions, then that they will insulate under other temperature conditions. An element that is on the metalloid line is aluminum, but it's generally not considered to be a metalloid because it has such strong metallic properties. And I'm not going to go over each of the groups 13 through 16 for this reason, because you have the metalloids smack dab in the middle of them. So what we're going to do is kind of skip to group 17, which are the halogens. This begins with fluorine. They are the most reactive non-metals. They will combine easily with metals to form salts. A salt is simply another name for an ionic compound. The word halogen translates to mean salt former. The group itself is made of 2 solids, 1 liquid, and 2 gases at room temperature. And the 2 gases are fluorine and chlorine. The liquid is bromine, and yep, I think you can figure out the 2 solids. They have 7 valence electrons, which means that they are 1 away from being a noble gas. Unlike the alkali metals, however, they have to gain 1 electron to look like a noble gas. They could lose 7, however, that's not as easy to do as gaining 1 is. And then that brings us to the final group, group 18, which are known as the noble gases. You've heard me talk about them over and over. They are considered to be virtually non-reactive nonmetals. I say virtually because there are some compounds that contain noble gases. We'll talk about those a little bit later. They are stable because their outermost energy level is filled, helium having 2 valence electrons and neon down having 8 valence electrons. That means that they're happy. They don't want to react with anyone because they have the number of valence electrons that they want. Okie dokie, that brings us to trends. I do an activity with my students where they use straws and a 96 well plate to literally in 3D analyze some trends on the periodic table. So what I have them look at are density, melting point, atomic radius, ionization energy, electronegativity, and electron affinity. And what you see on this slide is Webb Element's 3D-ish representation of density within the periodic table. You can see that the density is not a true trend in that as you move across it increases, or as you move down it decreases, something like that. But what you can see is that the transition metals tend to have the greatest density. Intertransition metals are pretty high as well. Next slide is melting point, and I think you see carbon's way up there. But yeah, boy, that allotropic carbon that's diamond definitely has a pretty high melting point, doesn't it? And there's a slight trend as you move across and as you move down, but not a really clear one. So we don't really consider those to be great trends, but you can get some idea of what goes on with the elements by looking at it. So the first real trend we're going to look at is the trend that is seen with atomic radius. Atomic radius is exactly what it sounds like, the radius of an atom. It is half of the diameter of an atom. Well, it's hard to measure an atom's diameter because it doesn't have real distinct edges to it. So what is done to obtain an atomic radius is you make a homonuclear diatomic molecule. Homonuclear means the same nucleus. Diatomic means 2 atoms that have been bonded to make a molecule. So you make a diatomic molecule with the same 2 atoms, and you measure from nucleus to nucleus. Nucleus is very easily identified. You take that distance from nucleus to nucleus, which does equate to a diameter, and you divide by 2, and you magically get the atomic radius. So that's how all atomic radii were determined. I've given you on this slide just an example of rubidium. What we see with the trend in atomic size is something known as the shielding effect. The shielding effect is the decrease in the attraction between a nucleus and its valence electrons that's due to the blocking by the core electrons, which are the innermost electrons, the non-valence electrons. So the more core electrons we have, the greater the shielding effect is. Which means that as we look at atomic radius, as we move across a period, we have more electrons that are added to the same energy level. As we move down a group, we have more electrons that are added to farther and farther away energy levels. So the trend that we see then is that atomic radius will decrease going across a period. We're getting more core electrons that are in the same energy level, which means the valence electron is staying in the same energy level, and it's getting pulled a little tighter and a little tighter and a little tighter as we move across. As we go down a group, we're getting more core electrons, but they're in farther and farther away energy levels. So that poor valence electron just gets pushed farther and farther and farther and farther away from the nucleus. And literally we see that the atomic size or radius increases as we go down a group. The next slide, I've shown you another Webb Elements, little 3D-ish looking arrangement with cylinders, and you can, I think, clearly see that trend of atomic radius decreasing across a period and increasing going down a group. The transition metals are represented here, but as I told you, they have varying properties, so they can kind of be all over the place. We don't really tend to talk very much in at least a lower level chemistry class such as general chemistry about the transition metals atomic radii. The next trend I'm going to go over is ionization energy. Ionization energy is defined as the energy that is required to pull an electron from an atom or an ion. Since its energy is measured in an SI unit known as a kilojoule, and we measure a kilojoule per a certain amount of atoms, and that is per mole of atoms. And I'll explain what a mole is a little bit later. So the units are kilojoules per mole. So again, it's the energy required to actually reach in and pull an electron off. Now think about the atomic size trend, because I'm going to go back to this each time and let you use atomic size to kind of govern your justification for the other three trends. As we increase our atomic size, remember, we're going down a group. As we decrease atomic size, we're going across a period. So as we move across the period, the size gets smaller because the electrons are held on by the nucleus with more vigor, more energy. Well, what that translates into is if you want to pull an electron off of somebody that's far on the right side of the periodic table, you're going to have to use more energy. As you move down a group, remember, the size gets bigger. And that's because the nucleus doesn't really care. Those protons don't care about that poor valence electron that's living farther and farther away from the nucleus. And I mean, by the time you get down to francium, it just goes, well, you know, here, just take it. It really doesn't care. In other words, it doesn't cost much energy to get francium's valence electron. It would cost more to get hydrogen's valence electron. It would cost even more to get helium's valence electron. So you see on the next slide that I've given you some examples of what I give you: hydrogen, helium, and potassium's ionization energies. You see that it increases going across a period and that it decreases going down the group. And again, the next slide, you see the Webb elements image showing you the same thing. The next trend is electronegativity. Electronegativity is a term applied by Linus Pauling to express the ability of an atom within a molecule to kind of suck electrons in, to bring electrons closer to it. So what you need to ask yourself is, who wants to get more electrons? Well, as you move across a period, you have more and more electrons in the same energy level, and that means you're getting closer and closer to being a noble gas. Well, as you get to fluorine, fluorine's only one electron away from being neon, right, with its electron configuration. And that means that fluorine goes, well, yeah, I'd really like to have another electron. So it has a great tendency to attract an electron to itself, because then it can have an electron configuration that resembles that of neon. However, as you move down a group, remember, we're getting bigger atoms. The nucleus doesn't really care about its valence electrons. It says, yeah, take them. It doesn't want to get another electron. Why would it want to do that when it doesn't even care about the one that it has? So that means it has a very low tendency to attract electrons to itself. So on the next slide, you see I've given you hydrogen, fluorine, and francium's electronegativity values. Linus Pauling arbitrarily set fluorine as the highest electronegativity value, not considering the noble gases, mind you. Those of you who did the straw activity saw that noble gases do have electronegativities, and they can be higher than fluorines. But fluorine is generally regarded as the element that can react easily, with the highest electronegativity of 4.0. And that means everyone else's electronegativity value is set relative to fluorine. So hydrogen's is 2.1 and francium's is 0.7. And that poor old 0.7 means francium doesn't really want to gain another electron. You can see on the Webb elements diagram that electronegativity will increase as you go across, decrease as you go down. The final trend we're going to discuss is electron affinity, and it's oftentimes a very difficult one to understand because it has negative values, and we don't like to think of negative values as the number gets more negative as saying that that increases. But we have to think of it in terms of giving away more energy, if you will. So electron affinity is defined as the energy change that's associated with taking on an electron. Remember, ionization energy was the energy associated with pulling an electron off. This is essentially just the opposite. It's how much energy would I have to give you to take another electron in. Now think about that. Who is more willing to take an electron in? Would francium be, or would fluorine? Well, you should think about it and say, well, francium has its valence electron way out there in the 7th energy level. Golly, no, you'd have to pay it $1 gazillion to coax it into taking another electron in. Whereas fluorine says, I kind of like that idea. You'd have to pay me lots and lots of money, and I'd take it. So in other words, it's a commodity issue, right? So electron affinity is going to increase as you move across a period, because it means fluorine demands more money, if you will, which is energy, to take on another electron. It's real close to being a noble gas, so it says, yeah, you pay me 329 kilojoules for every mole. So that's the idea behind it. So on this slide, you see that you have hydrogen, fluorine, and cesium's electron affinity values given, and they're in negatives, which is explaining the transfer of the energy. And again, you have a web elements arrangement of the cylinders. On this next slide, I've shown you all 4 trends that I've gone over. You'll notice that atomic size is the only one that decreases as you move across, increases as you move down. The other 3, those being ionization energy, electronegativity, and electron affinity, all will increase moving across a period and decrease moving down a group. So now I have a slide that asks you to do some practice with these trends and arrange the following elements in order of increasing atomic size. I've given you chlorine, oxygen, fluorine, and polonium. So what you need to do is locate those elements, turn off the podcast, do the ordering using greater than or less than signs. I've asked you to arrange in order of increasing, so you'll say so-and-so is less than so-and-so is less than so-and-so, and so on. And then turn the podcast back on. We're going to do 4 of these practice things. Get used to clicking pause and then clicking start so you can hear me give you your answers. So the answers for this first trendy practice are that fluorine, what did I ask you to do? Atomic size is less than oxygen, which is less than chlorine, which is less than polonium. The next one says arrange the following elements in order of increasing ionization energy. I've given you boron, helium, lithium, and nitrogen. So pause the podcast, do it, and then turn it back on. So your answer to the second one is lithium's ionization energy is less than boron's, which is less than nitrogen's, which is less than helium's. The third trendy practice I have for you is arrange the following elements in order of decreasing electronegativity. Carbon, fluorine, francium, and lithium. Pause it, come back. Fluorine's electronegativity is greater than carbon's, which is greater than lithium's, which is greater than francium's. And the final trendy practice I have for you is arrange the following elements in order of increasing electron affinity. Cesium, potassium, rubidium, and sodium. Notice I made this one really nice for you. Turn it off or pause, come back to it, and your answer is cesium is going to have smaller electron affinity than rubidium, which is less than potassium, which is less than sodium. And that brings us to the final part of this PowerPoint presentation, which is how elements are made. So we have naturally occurring elements, which are atomic numbers 1 through 92, and we're going to say for right now that is excluding atomic number 43, which is technetium. You recall I said that earlier when I was talking about the transition metals. There are 3 other elements that occur so infrequently in nature that they're almost considered to be unnatural. It's not that they don't naturally occur, they're just found so infrequently, and those are praseodymium, acetine, and francium. So, I keep talking about poor old francium. There's so little of it on Earth that we just really don't care about it. It doesn't care about its valence electron. It's just sad, isn't it? These naturally occurring elements are made of stars, and they result from the reactions that occur, and it's essentially the leftover junk from when stars collapse on themselves. These reactions are usually fusion reactions. Fusion reactions are a primary source of energy that would be a wonderful thing for us to be able to harness. It's just a little hard for us to harness it these days. A typical fusion reaction that occurs on a star is that 4 hydrogen nuclei will fuse to make 1 helium nucleus. The mass of the helium nucleus that results is actually less than the mass of the 4 hydrogen nuclei that we add together. And what that means is that we've defied the first law of thermodynamics, that the energy of the universe is constant. It's the energy of the universe is constant. It's not that the mass is. You've heard the law of conservation of mass, and you've heard the law of conservation of energy, and we tend to say that they're the same thing. Well, mass wasn't conserved, but let me tell you, we got this little concept called E equals mc squared, where when I show you this nuclear equation on this slide, you see 4 and then hydrogen 1 nuclei. You see the mass number is 1, the atomic number is 1. When they come together and fuse, they make 1 helium-4 nucleus with mass number 4, atomic number of 2. The question mark is, what's there? Well, you should be able to determine that when I add my 4 hydrogen 1 nuclei's mass numbers, I get 4. And when I add my 4 hydrogen nuclei's atomic numbers, I get 4. I'm missing some atomic number. Well, that missing atomic number is actually energy, and we use the equation equals mc squared that Mr. Einstein introduced to us to be able to understand that energy can be equated with mass. E is energy, m is mass, and c is the speed of light. So if we take the mass of an object, multiply it by the speed of light squared, we can equate that with energy, is what that means. So fusion reactions are essentially going to exchange mass for energy. And those helium nuclei that end up forming with all that energy that's floating around end up going through another fusion reaction with some more helium nuclei or some more hydrogen nuclei. And they keep going through these fusion reactions until essentially the naturally occurring elements are formed. It's just this nice process that keeps feeding itself because of that energy that's formed. A star will, and these are just general terms, a star is pretty much going to die when it doesn't have any more fusionable matter, so that it can't make new elements, and therefore it runs out of energy. And then planets are thought to result from the conglomeration of a bunch of dead stars that come together, and they make that big blob of all these elements that we find on this particular planet. Man can perform fusion reactions. It's just very difficult for us to do because the temperatures are so high. But they were first performed in the 1950s and ended up resulting in what's known as the hydrogen bomb, the H-bomb. And because the temperatures are a little bit greater than 20 million degrees Celsius, we don't really have a container, a physical container that can hold a fusion reaction. So that's why a bomb is considered an uncontrolled fusion reaction in the case of the H-bomb. Well, the H-bomb was really a fission reaction, which is splitting nuclei, and a fusion reaction. It had an atomic bomb, which is a fission reaction that triggered the H-bomb, a fusion reaction, because you had to get the temperature so high to make the fusion reaction work that the fission reaction had to precede it. So when fusion reactions are actually produced by man, they are contained in what's known as a magnetic bottle. It's just a magnetic field that houses all that reaction, the energy. So that brings us to fission reactions that I just mentioned. You get the image. If not, just think about fission. Okay, fission reactions are going to allow us to make new elements because we'll end up splitting generally a heavier nucleus into smaller, lighter nuclei. It ends up producing a whole bunch of energy as well, and I'd say that you could understand it if you take those alpha particles that Rutherford messed with in the gold foil experiment and you got them moving really, really fast. They bump into something, they split it up. So an example on this slide is that you take a nitrogen-14 nucleus and hit it with a helium-4 nucleus, an alpha particle. You end up getting a hydrogen-1 nucleus as one product. And what you have to do is add your mass numbers on the left and make your mass numbers on the right equal it. So notice your mass number on the left is 18 as you add 14 and 4. But you only have 1 on the right side. So what's missing? You should deduce that's a 17 as a mass number. Add your atomic numbers on the left and you get 9, 7 plus 2. On the right side you only have 1, so you're missing atomic number is 8. Well, what element is atomic number 8? And you should look at your periodic table and determine that that is oxygen. So oxygen 17 was produced in this example of a fission reaction. E.O. Lawrence is a gentleman who developed the first cyclotron. The cyclotron is a device that enables particles to get going really, 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 really fast. Think of the super collider, the giant super collider that you've heard about in the news just recently. He developed this cyclotron in 1930, and by the way, he's a gentleman for whom Lawrencium is named. And then Madame Marie and Pierre Curie's daughter and her husband, Irene and Frederic Joliot-Curie, were the first folks to make normally stable isotopes radioactive by bombarding them or hitting them using the cyclotron. They did that in the 1930s. The truly synthetic elements, those that are above atomic number 92, are made by using fission reactions. But let's talk about the first truly synthetic element. It's an interesting story, and that means one that was not previously existent. The first one, very first one, was technetium. In 1937, technetium was created by taking molybdenum and hitting it with deuterons, which are particles that are some protons and a neutron. Technetium is not a part of what's known as a decay series of any radioactive element. So we hadn't seen it before. There was a blank spot in the periodic table at atomic number 43, so we just thought, that's really weird. I guess we just have this synthetic element sitting in the middle of the periodic table. And they made it. Well, lo and behold, in 1988, yes, that many years after, 51 years later, someone discovered technetium naturally occurring in a molybdenum mine in Colorado. So we can no longer say that technetium is a synthetic element. It is naturally occurring, but kind of like francium, you recall, and praseodymium and astatine, it's occurring so infrequently on Earth that anytime we need to use technetium, we tend to make it. It tends to be synthesized. Technetium-99, for example, is a radioisotope that's used in bone scans. It's a bone-seeking element. It shows where you have, for example, broken bone. It can end up flocking to that site. Okay, up to atomic number 100, you can fire what are known as nuclear bullets at existing nuclei and turn them into new elements or previously inexistent elements. Nuclear bullets consist of protons, neutrons, alpha particles, or beta particles. And as I've previously said, alpha particles are helium-4 nuclei and beta particles are just electrons. So again, that's up to through atomic number 100. So any element can be synthesized using nuclear bullets. Atomic numbers 93 through 100 are definitely always synthesized. They are not naturally occurring. But once you get to higher atomic numbers 101 and higher, they're made using whole nuclei of heavier elements than helium-4. So I've shown you on this particular slide an example of a carbon-12 nucleus being beamed at a curium-244 nucleus. In that case, we know that two neutrons, which is what the N with the mass number of 1 and the atomic number of 0, are kicked out, and that ends up forming nobelium-254, which is atomic number 102. So that's an example of a nucleus with an atomic number greater than 100 being formed by use of a whole nucleus larger than a nuclear bullet. Alrighty. So this one kind of went all over the place, I understand, and my last little tidbit here is that you got a lot of stuff to think about, but I hope it tends to make some sense. I enjoyed doing this with you and look forward to the next one. I just love teaching chemistry, love doing these podcasts. You didn't even get a kitty meow in the background. Oh, well, hope you have a great day. Thanks for listening.